Hello viewers, in today's session we are going to discuss the working rule how to find the intervals where a given function is concave upwards and concave downwards, and we'll also see the algorithm or the method how to find the points of inflection of the given curve, right? So we have already discussed the concept of concave upwards and concave downwards, along with the concept of points of inflection in our earlier videos. So here we'll solve this problem, and we'll see the working rule, how to find the range of values for which this function is concave upwards and concave downwards, and we'll also find the points of inflection of this curve. So let us quickly see the definition of concave upwards and concave downwards. So suppose we have a function, say y is equal to f of x, right? Now this function is concave upwards when the second derivative, that is d2y over dx2, is greater than 0 for all values of x in a given interval, say I, right? So a function is said to be concave upward when we have the second derivative, that is d2y over dx2 is greater than 0. That is, the second derivative is positive for all x belonging to some interval, say I, right? And the function is said to be concave downward when we have the second derivative, that is d2y over dx2 is less than 0 for all x belonging to some interval, say I, right? So we are given a function y is equal to f of x, and this function or this curve is said to be concave upward when the second derivative is positive for all x belonging to I, and this function or this curve is said to be concave downward when the second derivative is less than 0, that is, it is negative for all x belonging to I, right? And this function has points of inflection when we have the second derivative, that is d2y over dx2 is equal to 0. So for the points of inflection, the second derivative must disappear, or it must vanish, right? So for points of inflection, the second derivative should be equal to 0, and here we have one more condition, that is the third derivative should not be equal to 0 for the values obtained by solving this equation, that is d2y over dx2 is equal to 0, right? So the working rule for getting the intervals where this function is concave upwards is given by this condition, and this function is concave downwards when we have this condition. And for the points of inflection, we have to first equate the second derivative is equal to 0, and then from this equation we find out the values of x, and then we find out the third derivative. And if the third derivative is not equal to 0 for the values of x obtained by solving this equation, then we can say that the given values of x obtained by solving this equation are the points of inflection, right? So here we can take this function as y is equal to f of x, and here we have this function. So let us first find out the first derivative, that is y prime, that is f prime of x. So here we have d by dx of x raised to 4 minus 6x cubed plus 12x square plus 5x plus 6. So here the derivative of x raised to 4 is 4x cube, and then we have minus 6. The derivative of x cube is 3x square. Then we have 12. The derivative of x square is 2x, and here we have the derivative of x as 1, and the derivative of 6 being a constant is 0. So we have 4x cube, then we have here 18x square, 6 times 3 is 18, then we have 24x, and here we have 5, right? So this is the first derivative. Now let us find out the second derivative. That is, here we have d2y over dx2. Here we have dy over dx, and here we have now 4 times the derivative of x cube, that is 3x square. Here we have minus 18, derivative of x square is 2x, and here the derivative of x is 1, and the derivative of 5 being a constant is 0. So here we have 0. So we have now the second derivative as 12x square, and then we have minus 36x, and here we have 24, right? Now let us find out the third derivative, that is d3y over dx3. So here we have now 12. The derivative of x square is 2x, and then we have minus 36, and the derivative of x is 1. Derivative of 24 being a constant is 0. So we have now 24x minus 36, right? So the working rule says that we have to first obtain the first derivative, the second derivative, and the third derivative, right? So now this function is concave upward. For the second derivative should be greater than 0. So here for concave upward, we must have y double prime is greater than 0. So this implies that we have 12x square minus 36x plus 24 should be greater than 0. So here now we have to solve this inequality. Here we have a quadratic polynomial, and here if we divide both sides by say 12, then we have x square minus 3x. Here we have 2, and this is greater than 0. So now we can easily factorize this quadratic function by splitting the middle term. So we have x square, then we have minus 2x, and here we have minus x plus 2 greater than 0. So we can now write x minus 2, and then we have minus 1 x minus 2, and this is greater than 0. So we have x minus 2 and x minus 1 greater than 0. So we can now write here x minus 1, x minus 2 greater than 0. So now we have here two linear factors, the product of two linear factors of this form, that is x minus alpha, x minus beta, and here we have greater than 0, right? So if we compare both these expressions, then we have alpha is equal to 1 and beta is equal to 2, and obviously here alpha is less than beta, that is 1 is less than 2. So here we have the real number line, minus infinity to plus infinity. Here we plot these 2 points, 1 and here we have 2, right? So the solution of this type of inequality, x minus alpha times x minus beta greater than 0, is given by x belonging to the interval minus infinity to alpha, and here we have the union, here we have beta to positive infinity, right? That is we have the solution as x less than alpha and x greater than beta, right? So the solution of this inequality is given by x belonging to minus infinity to 1, alpha is 1, union, then we have 2 to infinity, so here beta is 2, right? So this is the interval, or here this curve, this given curve is concave upwards in this interval, that is for all values of x which are less than 1, and for all values of x greater than 2. So this curve is concave upwards for all values of x less than 1 or x greater than 2. So here we have this region, that is x less than 1, and here we have x greater than 2, right? So in these two intervals, the given function is concave upwards, right? So now let us find out the intervals where this function is concave downwards. So now the function is said to be concave downward for all values of x for which the second derivative is less than 0, that is 12x square minus 36x plus 24 is less than 0. So we have this condition for concave downward, that is y double prime is less than 0, right? So we have seen that here we can divide both sides by 12. So we have x square minus 3x plus 2 is less than 0. So here we have factorized this quadratic function as x minus 1 and x minus 2, and here we have less than 0. So now here we have the real number line, and here we have the inequality of this form: x minus alpha, x minus beta is less than 0. So now in this case alpha is 1, beta is 2, and alpha is less than beta, that is 1 is less than 2, right? So whenever we have an inequality of this form, x minus alpha, x minus beta, the product is less than 0, then here we have 1, here we have 2, then the solution of this kind of inequality is given by x greater than alpha less than beta, that is x belonging to the interval alpha comma beta, right? So here the solution of this inequality, which is of this form, is given by x greater than 1, alpha is 1, beta is 2. So here we have 2, or we can write x belonging to 1 comma 2, right? So this is the region where this function is concave downwards, right? So this is the required interval where this function is concave downwards, and we have just seen that this function is concave upwards in this interval, that is from x belonging to minus infinity to 1, and then we have this interval that is 2 to infinity, right? So now let us find out the points of inflection. So let us see the working rule, how to find out the points of inflection of this given curve. So now we know that the point of inflection occurs at a point where the second derivative is equal to 0, and there is a change of concavity of the curve at that point, right? So it implies that the curve at this point, that is at the point of inflection, the curve goes from concave upward to concave downward, or concave downward to concave upward, right? So at this point, that is the point of inflection, the second derivative should be equal to 0. So here we have to now equate this expression, that is 12x square minus 36x plus 24 should be equal to 0. That is, the second derivative is equal to 0. So here again, dividing both sides by 12, we have x square minus 3x plus 2 is equal to 0, and we have seen the factors of this quadratic expression, that is x minus 1 and x minus 2 is equal to 0. So from here we have x minus 1 is equal to 0, x minus 2 is equal to 0. So we have x is equal to 1 and x is equal to 2, right? So solving this equation, d2y over dx2 is equal to 0, we have obtained two roots, right? And here let us now find out whether the third derivative is not equal to 0, right? So here we have the third derivative, that is 24x minus 36, right? So let us first take this point, that is x is equal to 1. So the value of the third derivative at x is equal to 1 is given by 24 times 1 minus 36, substituting x is equal to 1 over here. So we have 24 times 1 minus 36, that is 24 minus 36, that is minus 12, and which is obviously not equal to 0. And let us find out the third derivative at this point, that is x is equal to 2. So we have 12 times 24 times 2 minus 36, that is 48 minus 36, that is equal to positive 12, and which is also not equal to 0. So here we see that the third derivative is not equal to 0 for x is equal to 1 and for x is equal to 2. And these two values are obtained by solving this equation, that is, the second derivative is equal to 0. So at the point of inflection, we must have the second derivative is equal to 0, right? So here we can now claim that the points of inflection are given by x is equal to 1 and x is equal to 2, right? So these are the 2 points, that is x is equal to 1 and x is equal to 2, which are the points of inflection of this function, right? So viewers, this is the working rule, how to find out the range of values of x, or the intervals where the given function is concave upwards or concave downwards, and how to find the points of inflection. So now let us consider this problem. Here we have to find the intervals where this function y is equal to f of x, that is x cube minus 1, is concave upwards and concave downwards, and we have to also find the point of inflection, right? So here we'll follow this working rule. So here the function is y is equal to f of x, that is x cube minus 1, right? So here we'll first find out the first derivative, that is y prime. So here we have y prime, that is dy over dx, that is dy dx of x cube minus 1. So the derivative of x cube is 3x square, and here the derivative of 1 being a constant is 0. So let us find out the second derivative. So we have d2y over dx2, that is 3 times the derivative of x squared. So we have 3 times 2x, that is 6x. And then we'll find out the third derivative, that is d3y over dx3. So here we have 6 times the derivative of x. So that is 6 times 1, that is equal to 6, right? So we have this function y is equal to x cube minus 1. We have first uh, calculated the first derivative, then second derivative, and then the third derivative. So now this function is concave upwards when we have this condition, that is the second derivative d2y over dx2 is greater than 0. So here the second derivative is 6x. So 6x must be greater than 0. So here dividing both sides by 6, we have x greater than 0, right? So the function y is equal to x cube minus 1 is concave upward when we have x greater than 0, right? So here the domain of this function is the set of all real numbers, and here x greater than 0, or we can also write it as x belonging to 0 to infinity, right? And this function is concave downwards when we have this condition, that is the second derivative is less than 0. So we have 6x less than 0. Dividing both sides by 6, we have x less than 0, right? So for all x less than 0, the function is concave downwards, and we can also write it as x belonging to the interval minus infinity to 0, right? And for the point of inflection, we must have this condition, that is if the second derivative is 0 and the third derivative is not equal to 0. So the second derivative is 6x. So for the point of inflection, the second derivative must vanish here. So here we have 6x is equal to 0. So from here we have x is equal to 0, right? So now let us see this condition, that is the third derivative should not be equal to 0, and here the third derivative is equal to 6, right? So the third derivative is independent of x, right? So it doesn't depend on the values of x. So the third derivative at this point, that is x is equal to 0, it remains 6, and this is obviously not equal to 0, right? So this point x is equal to 0, it satisfies these two conditions, right? So the point of inflection of this curve is given by x is equal to 0, and here the third derivative is not equal to 0. At this point x is equal to 0, right? So here we have the real number line minus infinity to plus infinity. Here we have this point x is equal to 0. So from minus infinity to 0, that is in this interval, we have x less than 0, and the given curve is concave downwards in this interval, and in this interval we have x greater than 0. So the given curve is concave upwards, that is x is greater than 0, and at this point x is equal to 0. This curve has the point of inflection, that is x is equal to 0 is a point of inflection. So this implies that the concavity, it changes when we go from x less than 0 to x greater than 0, or from x greater than 0 to x less than 0. So now let us see how the concavity changes at the point of inflection, right? So we have just defined that at the point of inflection, we have the second derivative is equal to 0 and the third derivative is not equal to 0, and there is a change of concavity of the curve at the point of inflection, right? So either the curve changes from concave upward to concave downward, or from concave downward to concave upward, right? So let us see how the concavity changes at this point, that is x is equal to 0, which happens to be the point of inflection of this curve, right? So for this we have to make use of the second derivative, right? So the second derivative is f double prime of x. So here we'll use this notation, that is f double prime of x, and here we have 6x. So here we have x is equal to 0, right? So let us take 2 points, one towards the left and one towards the right, and the 2 points are very close to x is equal to 0. So let us take 2 points in the neighborhood of x is equal to 0. So here we have the point, say 0 minus h, and here we have the point 0 plus h, right? And let us see the behavior of the second derivative when we go from 0 minus h to 0 plus h, right? That is crossing x is equal to 0. So when we make a transition from this point 0 minus h to 0 plus h, passing through x is equal to 0. So let us find out the sign of the second derivative at this point, that is 0 minus h. So here we have f double prime, here we have 0 minus h, right? So we have 6 times 0 minus h, taking x is equal to 0 minus h. So here we have minus 6h. And remember, h is infinitesimally very small, and it is always a positive quantity, right? So h is greater than 0. So this quantity is less than 0. That is, it is negative because h is positive, right? So the second derivative is negative. That is, it is less than 0 when we have the point towards the left of x is equal to 0. So let us now find f double prime of 0 plus h, that is this point 0 plus h. So we have 6, here we have 0 plus h, and here we have 6h. Now h is positive, so 6h must be positive. So here we have a greater than 0. So when we make a transition from this point to this point, passing through x is equal to 0, then the second derivative here is greater than 0, right? So when we go from this point to this point through x is equal to 0, then the second derivative, that is f double prime of x, it changes sign from negative to positive, right? So here the transition is from negative to positive, right? Because here we have less than 0, here we have greater than 0, and we have just seen that the uh, function or the curve is concave downward when we have the second derivative less than 0, and concave upward when the second derivative is greater than 0, right? So here the concavity it changes from downward, because here we have negative and here the second derivative is less than 0, that is negative, right? So the concavity changes here. That's why x is equal to 0 is a point of inflection, right? So here the concavity changes from downward to upward, right? Hence, this point x is equal to 0 is a point of inflection, because here in the neighborhood of x is equal to 0, the second derivative changes sign from downward to upward. And from the definition of point of inflection, we know that a point of inflection occurs at a point where the second derivative is 0, right? And when second derivative is 0, we have the point x is equal to 0, and there is a change of concavity of the curve at that given point, right? That is, the concavity changes either from upward to downward or downward to upward, right? So the concavity of the curve implies that how the curve bends, right? So here the concavity changes from negative to positive. That's why x is equal to 0 is a point of inflection, right? So this is the working rule how to show that the concavity changes. So when we solve this equation, the second derivative is equal to 0, we get some values of x, that is the roots of this equation, and then one by one we test the roots for these conditions, right? And in this case, the concavity changes from negative to positive, therefore x is equal to 0 is a point of inflection. So now let us consider this problem. Here we have to find the intervals where this function is concave upwards, concave downwards, and we have to also find the point of inflection, right? So here the equation of the curve is x cube minus 3x square plus 3x plus 4. So let us first find out the first derivative. So y prime is given by here f prime of x, because this is y is equal to f of x. So we have here 3x square, then we have minus 3 times 2x, then we have 3 times 1, and the derivative of 4 is 0. So we have 3x square minus 6x, and then we have here plus 3. Now the second derivative is f double prime of x. So here we have 3 times 2x. The derivative of x square is 2x. Then minus 6 times 1 plus 0. The derivative of 3 is 0. So we have here 6x minus 6. And the third derivative, that is f triple prime, is given by 6 times 1. The derivative of x is 1. Here the derivative of 6 is 0, so we have simply 6, right? So we have obtained the first derivative, the second derivative, and the third derivative, right? So now this function or this curve is concave upward when the second derivative is greater than 0. So here the second derivative is 6x minus 6, right? So y double prime must be greater than 0 for the function to be concave upwards, right? So 6x minus 6 must be greater than 0. Dividing both sides by 6, we have x minus 1 greater than 0. So from here we have x greater than 1. So this function is concave upwards when we have x greater than 1, that is x belongs to the interval 1 to infinity, right? And this function is concave downwards when the second derivative is less than 0, that is 6x minus 6 is less than 0, right? So from here we have now dividing both sides by 6, we have x minus 1, that is less than 0. So from here we have x less than 1. So this implies x belonging to the interval minus infinity to 1. So this function is concave upwards when the second derivative is greater than 0, that is when x is greater than 1 or x belongs to 1 to infinity. And this function is concave downwards when we have second derivative less than 0, that is x less than 1, that is x belonging to minus infinity to 1. So here we have minus infinity plus infinity, here we have x is equal to 1. So here we have x less than 1. So the function is concave downward, and here we have x greater than 1. So the function is concave upwards, right? So let us now find the point of inflection. So the following the working rule here for the point of inflection, if the second derivative is 0, so here the second derivative y double prime is equal to 0, that is 6x minus 6 is equal to 0, 6x is equal to 6, x is 6 over 6, that is 1, right? So we have x is equal to 1. So let us now find out the third derivative. So here the third derivative is 6, right? So the third derivative is independent of x, right? So at this point x is equal to 1. The value of the third derivative, it remains 6, which is not equal to 0, right? So this condition is also satisfied. So we can now say that x is equal to 1 is a point of inflection, right? So here we have x is equal to 1 as the point of inflection. And remember, at the point of inflection, the concavity, it changes either from concave upward to concave downward, or from concave downward to concave upward, right? So let us now see the working rule, how to show that at x is equal to 1 the concavity changes. So for this we have to make use of the second derivative, the expression for second derivative. And here we'll see the sign of the second derivative in the neighborhood of x is equal to 1. So now here we have the point x is equal to 1, which happens to be the point of inflection, right? So here we'll take 2 points in the neighborhood of x is equal to 1, right? So one towards the left and one towards the right. So here we have 1 minus h, here we have 1 plus h. So this point is 1 minus h, and this point is 1 plus h, and here h is infinitesimally very small, and here h is a positive quantity that is greater than 0, right? So here we have y double prime, that is f double prime x is equal to 6x minus 6. So let us take first we take x 6 common, so we have 6 times x minus 1. So let us now calculate the value of second derivative at this point, 1 minus h. So taking x is equal to 1 minus h, over here we have f double prime 1 minus h, and here we have 6, and here we have 1 minus h minus 1. So 1 and minus 1 get cancelled, we have minus 6h, and h is greater than 0, so this quantity is going to be negative, that is less than 0, because this product 6h is positive because h is greater than 0, but here we have a negative sign, so this entire term minus 6h is less than 0. And then we find out the sign or the value of the second derivative at this point, 1 plus h. So we have f double prime 1 plus h. So here we have 6, and then we have here 1 plus h minus 1. 1 and 1 get cancelled. So we have here 6h, and h is greater than 0. So this product is obviously greater than 0. So we see that in the neighborhood of x is equal to 1, the sign of the second derivative is changing from that is negative. So here we have a negative and here we have a positive. That is, the second derivative is less than 0, negative. Second derivative is greater than 0, positive. So here the sign of second derivative is changing from negative to positive. And we know that the curve is concave downward when the second derivative is less than 0, that is negative, and the curve is concave upward when the second derivative is greater than 0, that is positive, right? So here the concavity changes when we go from that is when we make a transition from 1 minus h to 1 plus h, that is from left to right, uh, going through x is equal to 1. So here the concavity changes from concave downward to concave upward, right? And we know that at the point of inflection there is a change of concavity, that is the curve bends, right? So here we have concave downward, here we have concave upward. So we have the shape of the curve like this, that is here we have the concave downward, and then we go like this, and here we have concave upward, and here we have concave downward, right? So here we have the point of inflection, right? So at the point of inflection, let us say this point as P. So and this point is x is equal to 1, right? So this point P is the point of inflection, and here the concavity changes from concave downward to concave upward, right? So this is how we can prove how the sign of second derivative changes, or the concavity changes when we in the neighborhood of the point of inflection. So now consider this problem. Here we have to find the points of inflection of the function y is equal to f of x, that is sine x, right? So here we have drawn a rough sketch of the function sine x. So here we have plus 1, here we have minus 1, and here we have 0. This is pi by 2, this is pi, then we have here 3 pi by 2, and here we have 2 pi, and so on, and here we have minus pi by 2, and here we have minus pi, and here we have minus 3 pi by 2, and here we have minus 2 pi, right? So this is the graph of sine x. So let us find out the points of inflection, right? So we'll follow this working rule. So let us first find out the first derivative of sine x. So y prime is f prime of x, that is d by dx of sine x, that is equal to cosine x. Then we find the second derivative, and here the derivative of cosine x is minus sine x. And then we find out the third derivative, and here we have minus the derivative of sine x is cosine x, right? So for this function y is equal to sine x, we have the graph, and then we have the first derivative, second derivative, and the third derivative. So now for the points of inflection, we have this condition: if the second derivative is equal to 0, and the third derivative is not equal to 0. So here we can equate y double prime is equal to 0 to get the points of inflection. So we have a minus sine x equal to 0. So from here we have now sine x is equal to 0, and the solution of this trigonometric equation, that is sine x is equal to 0, we have x is equal to n pi, right, where n it belongs to the set of integers, right. So here we have n is equal to 0, plus minus 1, plus minus 2, and so on. So we can find out the points of inflection by taking n is equal to 0, plus minus 1, plus minus 2, and so on. So here taking n is equal to say 0, we have 0 times pi, that is equal to 0. So x is equal to 0 is one point of inflection. Similarly, for n is equal to 1, we have x is equal to 1 pi, that is simply pi. For n is equal to 2, we have x is equal to 2 pi. And similarly, for n is equal to minus 1, we have x is equal to minus pi, right, and so on. We can go on substituting the values of n in this equation, and we can get the points of inflection, right. And here the third derivative, that is y triple prime, that is minus cosine x. So for x is equal to 0, we have the third derivative, that is minus cos 0, right. So taking x is equal to 0. So here we have cosine 0 is 1, so we have minus 1, and which is not equal to 0. So x is equal to 0 is one point of inflection, right. So here to get the point of inflection, we have equated the second derivative equal to 0, and getting this expression x is equal to n pi, taking n 0, plus minus 1, plus minus 2, and so on. We have the points of inflection as 0, pi, 2 pi, and then 3 pi, and so on, right. So for this point x is equal to 0, we have seen that the third derivative is not equal to 0. Similarly, for x is equal to say pi, we have the value of third derivative, that is x is equal to pi, we have minus cosine pi, right. So here we take x is equal to pi. So the value of the third derivative at this point, x is equal to pi, is minus 1. Cosine pi is minus 1. So here we have plus 1, which is not equal to 0. So similarly, for say x is equal to minus pi, we have the third derivative equal to negative of cosine minus pi. So we have minus cosine pi, because cosine minus theta is equal to simply cosine theta. So here cosine pi is minus 1, so this is plus 1, that is not equal to 0. So similarly, for other values of x, that is for other values of the points of inflection, we can show that the third derivative is not equal to 0, right. So we have the points of inflection as x is equal to 0, then taking n is equal to plus minus 1, we have plus minus pi, then we have plus minus 2 pi, plus minus 3 pi, and so on. So these are the points of inflection of this curve, that is y is equal to sine x, right. So let us now take x is equal to 0, and let us see how the concavity changes when we take this point of inflection x is equal to 0, right? Because we know that a point of inflection, it occurs at a point where the second derivative is 0, and there is a change of concavity of the curve at that point, right? Then only we can say that the particular point is a point of inflection. So let us now see the change in concavity at this point. X is equal to 0. So now let us find out the change in the sign of the second derivative in the neighborhood of x is equal to 0, right? So here we have x is equal to 0. So here towards the left we can take the point 0 minus h, and here towards the right we can take 0 plus h. So here we have x is equal to 0. So here we can take this point as 0 minus h, and here we can take the point 0 plus h, and obviously h is greater than 0 because this is a positive quantity and it is infinitesimally very small, right? So let us see the change in the sign of the second derivative in the neighborhood of x is equal to 0. So now here we have f double prime, and first we'll take x is equal to 0 minus h. So here we have 0 minus h. So we have minus sine of 0 minus h, right? So this is minus sine minus h, and this is negative of sine h, because we know that sine of minus theta is equal to minus sine theta, right? So this is now positive sine h, right? And then we take x is equal to 0 plus h. So here we have a 0 plus h. So f double prime 0 plus h, and we have minus sine taking x is equal to 0 plus h. So we have 0 plus h, and here we have minus sine h, right? So the second derivative at this point, that is 0 minus h, is positive sine h, and the second derivative at this point, that is 0 minus that is 0 plus h, is negative of sine h. So when we go from 0 minus h to 0 plus h through x is equal to 0, then see here the second derivative is positive sine h, right? And h, it belongs to the first quadrant, and h is infinitesimally very small, and in the first quadrant sine function is positive. So here this quantity, that is sine h, is positive, right? And here the second derivative f double prime 0 plus h is negative of sine h. Now since sine h is positive, because h belongs to the first quadrant, and in the first quadrant sine function is positive, so sine h is positive, and here we have negative, so this quantity is going to be negative, right? So here we have negative. So when we go from 0 minus h to 0 plus h through x is equal to 0, then the sign of the second derivative, it changes from a positive to negative, right? Positive to negative. So now here the second derivative has the sign positive, and the curve is said to be concave upward when the second derivative is greater than 0. That is, the second derivative is positive. So here we have concave upward, right? And here the sign of the second derivative is negative, and when the curve is concave downward, we have the second derivative less than 0, right? So here we have concave downward, right? So when we take this point, that is x is equal to 0, which is the point of inflection, then the concavity changes, right? So when we go from this point to this point through x is equal to 0, then the concavity changes from concave upward to concave downward. Therefore x is equal to 0 is a point of inflection, right? So here the shape of the curve is like this, that is we have like this, right? So here we have the sine curve, it goes like this. So here we have the point x is equal to 0, right? So here we have concave downward, and here we have concave upward. So this is concave upward, and this is concave downward, right? And x is equal to 0 is the point of inflection, right? So this is how we can see, or we can prove the change of the sign of second derivative at this point of inflection, that is x is equal to 0. So we can adopt a similar method for other points also. So let us now take x is equal to pi. So now here we have x is equal to pi, right? And we can take this point as pi minus h, and this point as pi plus h. So here we have pi. So here we can take this point as pi minus h, and this point as pi plus h, right? So we have now the second derivative at this point, x is equal to pi minus h. This point is pi minus h. So f double prime pi minus h is now equal to negative of sine of pi minus h, and we know that sine pi minus theta is equal to sine theta, right, from trigonometry. So here we have minus sine h, and for x is equal to pi plus h, we have f double prime, here we have pi plus h, and this is negative of sine pi plus h. And from trigonometry we know that sine pi plus theta is equal to negative of sine theta. So here, so now here we have a negative, this is the negative sign, then sine pi plus h can be written as negative of sine h, and this becomes positive sine h. And we know that sine h is greater than 0, that is sine h is positive because h, it lies in the first quadrant, right? So sine h is positive, and here we have negative, so this quantity is negative, right? And here we have positive sine h, and sine h is positive, so this entire quantity is positive. So here when we go through x is equal to pi, from pi minus h to pi plus h, right? Then the sign of the second derivative, it goes from negative to positive, that is the sign of the second derivative changes from negative to positive. And when the second derivative is negative, then we have the curve as concave downward. So here we have concave downward, and here we have positive, the sign of the second derivative is positive, and for the second derivative to be greater than 0, we have concave upward. So here we have a concave upward, right? So here, when we make a transition through x is equal to pi, from pi minus h to pi plus h, the concavity changes from concave downward to concave upward, right? So here we see that this point is pi minus h, and this point is pi plus h. So here we have pi plus h. So when we go from pi minus h to pi plus h, then here the shape of the curve, it goes like this, right? So here this is a concave downward, and here we have the curve like this. So this is concave upward, right? So the concavity changes from concave downward to concave upward at x is equal to pi. So x is equal to pi is a point of inflection, right? So similarly, we can make the exploration for other points also, right? So this is how we can find out the points of inflection of this curve y is equal to sine x.